Hello, and welcome to this quick video about floating point numbers and the dangers of floating point numbers. So, floating point numbers are these floats types numbers with decimals, basically. And a thing you should be aware about them is that they're not exactly the number that you think they are. They're sort of always an approximation. So the reason for this is if you can remember the real line of all real numbers from your math class, the sort of the line where you have the negative numbers and positive numbers, and then 0, 0, 1, 2, 3, 4, 5, and then all the numbers in between are sort of the decimal numbers. And if you can remember those, then you can also remember maybe that there are infinite decimal numbers, because there are infinite points on that line. Then you sort of look at, okay, that's 0.35, that's 0.356, and you can do that infinite many times. And computers don't really like infinity because it have finite memories. So what they do instead is they can approximate these infinite many numbers by a finite number of numbers. The way the computer does this in practice is it approximates the number using something called a significand, which is basically 1 or minus 1. So just is this a negative or positive numbers, and then it approximates the numbers by taking an integer and to the power of another integer. For a 64-bit number, this is sort of the bits are the 0 and 1s the computer uses to store integers. Then you have the significand takes up 1 bit, the base takes up 52 bits, and the exponent takes up 11 bits. And this is a finite approximation, but it gives a lot of different numbers, and it also gives you can go from minus a huge number to plus a very, very huge number. But you cannot represent all numbers exactly. So what happens in practice if you create a floating point number, for example, that you call 0.1, then it's not exactly 0.1. If you, for example, print 100 decimals, then you will see, okay, there are actually some non-zero decimals at some point. It's not important. In practice, you still have sort of, okay, this is still 0.1. It's just very tiny bit smaller than 0.1. But you should note it when programming, because it can sort of create problems for you later. The exact same with 17.2. It's a tiny bit smaller than 17.2 when Python stores it. What can happen in practice is, for example, that if you start with 0 and then you add 0.1 10 times, then that should be 1, but Python's not. This is not exactly 1, it's 0.999 because of the way it stores these approximations. Another thing that is, and this is pretty dangerous and it can sort of happen a lot, is that you shouldn't test whether or not floating point numbers are equal to each other using the equal sign. Because, for example, if you say 0.1, is that equal to 0.1, a bunch of zeros and then 1, so something tiny bit smaller than 1, you say, okay, is this equal to each other? Then Python will actually say, yeah, that's equal to each other, even though it's not exactly equal to each other. And the opposite can also happen a lot. So you can have, so this is what happens here. If we take this formula, which sort of says that a times c divided by b times c is equals to a divided by b, and that's sort of, it's maths, you can't really argue with it, but Python will try to argue with it and say, no, you test the equality, okay, is this true? No, it's not true, Python will say. Again, because of these approximations of floating point numbers. A thing to deal with this in practice is to round off the numbers. So you use this inbuilt function called round, which basically just round the number down to 10 decimals, so I can show you what pops out of it. And then you can test, okay, are these numbers equal to each other? And then Python will be like, yeah, they are actually equal to each other if you round them down to the decimals that we care about as humans. A more common approach to this is used inbuilt function of NumPy called isClose, which tests whether or not two numbers are close to each other. And it's sort of their inbuilt keyword arguments for like what is the tolerance of when two floats are practically the same, sort of. For the purposes we care about, you would typically just use the keyword arguments to say, okay, these two are very, very close, and close enough for like most humans would just say they are the exact same. But again, Python would not. You have to use this isClose. Two other issues you can have is called underflow and overflow. These are not like, it will rarely happen in practice, but it's good to know that it can happen. So underflow is that if you have a very, 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 very small number and you want to represent it, then Python will sometimes store it as an exact zero number. So here we're just taking the number 1 and we multiply it by a very small number, and then we print it each time and see what it is, or what Python stores it as. So it starts up great. It's becoming a smaller number. But at some point, Python will say, this is exactly 0. And we know it's not exactly 0, because two numbers that are not 0 multiplied by each other are not 0. But it sort of, Python stores it as 0 because it just becomes so small that it cannot be approximated by the formula we saw at the beginning of the video. And the same problem can happen at the other end. It's called the overflow, that if you want to represent a really, really, really large number, then at some point Python will just call it an infinite number, even though it's a finite but extremely large number. So this is sort of represented by this loop, where we just multiply numbers to both x and y, and then at some point they become infinite. And then this formula also doesn't hold anymore. This is basically the same formula as up here, where c is just it's just done multiple times. Here you should still have that y divided by x is the same as 2.1 divided by 1, so it should be 2.7. But it's not, because both of these numbers are now stored as infinite numbers. Yeah, so a non is not a number and inf is infinite. Another thing that can be important or should be aware of is that sort of order of additions matter. So the order of how you add the numbers up can sort of create small differences in what the sum becomes. So here we have that the difference between these two numbers, although the difference should be 0, it's just an extremely small number. That's the difference instead. So yeah, that's floating point numbers and their dangers. They're approximate. You should never compare them using equality signs. You should use greater than or smaller than, or this NumPy function isClose. And then we talked about underflow and overflow. If you want more details, you can look at them here. There are also some more entertaining videos about floating point numbers. Thank you for watching.